Hello everyone, this is Trisha Naik from TE Electronics and today I'm going to be designing a differentiator in LTSpice. So first let us do the calculations for our resistors and capacitors. So here I am considering my FA to be 1 kilohertz and FB to be 10 times of FA, which is 10 kilohertz, and I'm assuming my C1 to be 0.01 microfarad. So the formula for FA is 1 upon 2 pi RF C1. So we can write FA to be 1 upon 2 pi FA C1. If I calculate using these values, it comes out to be 15.91 kilo ohms, and I've taken 16 kilo ohms as the standard value. Similarly, the formula for FB is 1 upon 2 pi R1 C1. Therefore, my R1 comes out to be 1 upon 2 pi FB C1. So now I can, and my R1 comes up to be 1.6 kilo ohms. For my ROM, which is my compensation resistor, I've taken, it has to be R1 parallel RF. So I can take this as 1.5K, which is a standard value. Mine actually turns out to be 1.45 kilo ohms. So for the value of the feedback capacitor, if we assume R1C1 to be equal to RFCF, we can find RFC1 CF, which is R1C1 upon RF. Therefore, my CF comes up to be 0.001 nanofarad. Now to implement and design this circuit, I will first start by clicking on component and getting an OP07 here. Now I'm going to be getting all my resistors. I can use this button to rotate it. I need one for input, one for feedback, and I'm going to be needing one for the compensation as well. Now for the capacitors, I'm going to rotate the capacitor as well, one at the input, one for feedback. Now I'm going to be giving the voltage sources. So I go to components and type in volt. This is my V1, and I also need two more to give input to the op amp as well. Now I'm going to be joining these using wires. I'm going to be taking out a VO, and I'm joining my feedback paths as well. Connecting my resistor also. Now I also need to connect my non-inverting terminal. Now I'm going to connect my grounds here and here as well. Now I need to give ground here, as well as I need to join these with wires. And here. Now I'm going to label my input and output. I can right click here, go to label net and say VN and connect it here. Similarly, I'll right click here, go to label net and say Vout and connect it here. Now I need to label these points as well, since I'm using them to power my op amp. So I'm going to take out wires from here as well, and I need to label these as VCC. I'm going to connect VCC here as well as here. Similarly, I'm labeling this as VEE, connecting it here as well as here. Now I need to give the value to the components. So this is my Rn or R1, which was 1.6 kilo ohm. My feedback resistor, which was 16 kilo ohm. My input capacitance, which we can also call as Cin, which was 0.01 microfarad. And this is my feedback capacitance, which was 0.001 nanofarad. Yeah, so our circuit should be ready. Now to give the input, I can right click over here and go to advanced. Before that, we need to give these values. So since this is for the op amp, we can give a value of 15 volt on either of the inputs. Yeah, so here we go and right click, go to advanced, and first we are going to check the output for a sine wave. So here I click on sine. I want a 0 DC offset. I'm giving a sine wave of 1 volt, that is 2 volt peak to peak, and a frequency of 1 kilo. We also saw that my R compensation was R1 parallel R2 or RF. If we want, we can label this as well. And which came out to be 1 kilo. Yeah, so when I run this, it's going to ask me for a stop time. So I'm going to put in a stop time of 10 millisecond and check the input as well as the output. So if I see here, for a sine wave input, I get a cosine as the output. We can also change this. I can make this 5 millisecond and run again. If we want fewer cycles, it will stop at 5 cycles. So similarly, let us check the output for a square wave input as well. For a square wave, we need to choose the pulse option over here, and given our amplitudes, so I'm going to start with -1 and keep this as 1. My delay is going to be 0, rise is going to be 0, fall is going to be 0 as well. I'm keeping T on as 100 micro, and my T period should be double of it, which is 200 micro. And I'm going to click on OK. I can use this to drag my values, and now I'm going to run this. This is my square wave, and I can see that I'm getting spikes at the output. To make this a bit more clearer, let us run this like this. So we can see that we are giving a square wave as the input and getting spikes as the output. Now to give a triangular input, we again go to click pulse, but this time our T rise will have a value. I'm giving it as 1m. So my T rise will be equal to T fall if I'm giving it. So 1m for both. I'm giving this as 0 and give this as 2m, which is a double of this, and click on OK. This should give me a triangular wave. Check the input again and the output. So for this, I'm going to increase the time and make it 10 millisecond and run again. So now I can see that for a triangular input, I'm getting a square wave at the output. For the output, my green is the input and my blue is the output. Now for the frequency response, we click on none, and here in the box saying amplitude, I'm putting in 1, which is 2 volt peak to peak, and I'm going to remove this, and now I'm going to run. In the simulation command, I need to click AC analysis. I'm going to select octave. My start frequency I'm going to put in as 100 Hz, and my stop frequency as 100 kilohertz, for example, and I'm going to say 100 points per octave and click on OK, and I'm going to check my output. So this should give me my frequency and phase plot in the same graph. So if I want to check only the frequency plot, I have to right click here and click on don't plot phase. So this should give me only the frequency. Similarly, if I want to check only the phase, I right click on this again and click on OK. My phase will be visible. To remove the magnitude, I just click on don't plot the magnitude and I should see only the phase plot. So now to take readings as I have taken them, this is a table I have created. My FA is 1 kilo ohm and my FB is 10 kilo ohm. So and these are the frequencies at which I've observed these parameters, which is V out, gain and gain in decibel. So to check these, I'm going to get my magnitude plot back first and remove my phase plot. I can right click here and click on linear. This should give me my V out. If I want to check for values beyond 1 kilohertz, I can right click here and manually change the limits. If I place my cursor here on my left bottom corner, I can see the values given. Similarly, to check the gains, I have to go to plot settings and go to add trace. Here gain is always V out upon V in, so I'm going to click on V in upon V out upon V in and click on OK. This should add this trace. Now for gain in for this column, the output, my output is similar to the V out. So similarly, I can place my cursor at any place and check the values here and enter them in my table. Now for gain in decibel, I can right click here again and go to decibel and click on OK. This gives me my gain in decibel, and again I can place my cursor wherever I wish to get the values. So I can see that I've designed for 1 kilohertz. So if I place my cursor on 1 kilohertz, I get a 0 dB. So in this way we have designed a practical differentiator, and we have observed the frequency response, the phase plot, as well as the outputs for various inputs of sine, square and triangular. Thank you.